Good, thanks. How are you?
Oh, pretty good. Pretty good. I get my screen sharing here, and I'm recording. And what should we start with today? Do we want to look over some questions from yesterday, or what's up? Anybody?
Yeah, sorry, I'm just flipping to my page.
Can load up. Was it 16 and 17? Is that right? 18. Yeah, 16 and 17. 16 answers. Have them handy, so if you ask a question, it's easy for me to look through with you.
Can we do 8B on 358? That's the first lesson, maybe?
Here.
Like lesson 16.
I think something's loading on my computer right now. There we go. 16 answers. And you said number 8, you said?
8B on 358. 8,
okay.
Yeah.
8B. Okay, so just to start out with, we probably should look at 8 first, or is 8 and 8B? Oh, I get it. Yeah, okay. I'll flip to my textbook page as well then, actually, so I can remember what they asked in each part. 358. 8. So we have these 3 charges, the corners of an equilateral triangle. They're showing you like a +4 at the top and a -4 at the bottom and a +2 at the bottom, always microcoulombs there. Lengths are 2 meters. So they want the total electric potential energy. So the first part was just add up the energies. So you have just pairs, right? So basically you've got the pair of the 1 and the 3, for example, and then the 1 and the 2, and then the 3 and the 2, and basically that's it. So you've got these pairs. It's not as complicated as a 4-sided figure, but yeah, anyway, so they added up as vectors. So that's part A, and you're good with that one apparently because you didn't ask about it. It does say then determine the electric potential at the middle of each side of the triangle. So the middle of each side of the triangle. So I'm looking at what I did here, and I don't know if I agree with what. Is that why you're asking, David? Is like, doesn't seem like I've answered what it's asking, or?
Yeah. I think also it got assigned like twice, and I think you have the answer maybe on the second lesson. I don't really know.
Yeah, because.
But I think that it got assigned for both lessons.
Yeah, because I don't know if I'm answering the same question here, actually, come to think of it, because the electric potential wasn't covered in this lesson, right? So basically, if I go back to lesson 16, I don't think I should have just assigned 8A, because we had only covered electric potential energy at that point, which makes me wonder what the heck I'm even looking at there then on this. Is it right or not? I've got the electric potential energies there. And then this one, I've gone and I've calculated the diagonals. I feel like I'm 1 from 2, 1 from 3. I feel like I'm calculating the force there, but it's still just energy. I don't know. I'll have to come back. I'll have to look at this one again. So I'm gonna just make a note to myself to look at what I was doing here. 1, 2, 1, 3, 1, 4. Like basically this, the way that's written out there, having all of these pairs like this, that's more if you're talking about force. I might have just gotten confused when I was doing this. So you got like those 3 pairs there. Now I only have then the 4 and the 3 as well, and the 4 and the 2. Let me come back to that one, and I'll start with that tomorrow morning. How about that? I'll just look into what I was thinking here and what I want to use as a final answer for what really should be done. How about that? Okay. I just feel like I need to put a little more thought into it.
Yeah, that's good. Thanks.
There. Yeah, no worries. So I'm gonna just write that down on a piece of paper so I don't forget. am a wee bit forgetful sometimes. 358, number 8. That actually says 18. Is that 8? Is this part of 8 or is this part of a different question? What the heck is that?
That's 18, but I didn't know how to do that one either.
So is that question 8? Where's that one from?
That's question 18. That's the last question on lesson 16.
Oh, yeah. Okay, so this is a rectangle. Yeah, okay. This actually, okay. I'm not quite with it yet this morning apparently, because I was honestly messed up in thinking that this was like the same one, but of course it's not. And so yeah, you have more pairs. So when you have pairs of size, so this was just 8A. Yeah, this is just 8A. It should have just been 8A. I don't recall whether I assigned it clearly like that or not. I might just load that lesson up while we're waiting here, just so I can make a correction if needed on my file. I'll load the copy one because that's the one I would use next time around. So then 18 is just looking for energy again. So you're talking about more pairs of charges when you're talking about a rectangle. So I might not need to do this tomorrow morning. So with the Q1, you'd be like, we've got that pair, that pair, that pair, and that's these 3 to start out with, right? And then you've got, I'll go with a different color to make it easy to follow here. Then from Q2, for example, you already have the Q1, Q2 pair. So you just have to acknowledge the Q2, Q4 pair and the Q2, Q3 pair, right? So the 4, I think I might have started with the 4 next. I'll do that as well as my picture. So the 4, I said, oh, you have to acknowledge that one. I've already done the Q1 4, and so then I've got those ones, 4-3 and 4-2, right? So that's those. And then finally, now the only other one that there is a pairing of energy associated with it is that. So this is totally fine. I don't need to deal with this tomorrow morning. After all, I was just super confused for a second there that I thought I was talking about 8B in this question, and it's not. It's 18, of course. So yeah, is that okay now then?
Yep.
So this is the one where I said, you can just common factor out, and you don't have to type in 9.0 times 10 to the 9 and 1.2 times 10 to the negative 3 and blah, 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 over and over and over and over again. You can just common factor those all out, and yeah, and then just get all of these divided by r's combined to be a 6.06 repeated and get your final answer. Yeah, so these are just energy, just 8A. So I don't know if my 16 came up yet or not in this, but this definitely should just have that 8A because we haven't done electric potential yet in that lesson. So that was my bad on that one for sure. So 8B we haven't done yet. Okay, and shouldn't have done yet. But like you said, it's going to be in the next question set. So let me load that one up too. And we can still answer other questions too with this one if anybody wants. 17 answers. And so we can see 8B in that one. And it'll make a lot more sense than question 18 does as a solution. Well, I thought I was confused then, but instead I was confused now. I'll wait for it to load up. Any other questions about lesson 16 homework though?
It's okay. You just covered the one that I had the question on, so it's good.
Perfect. Yeah, and it's really a case of just getting used to the idea that you've got this new equation that EE equals KQQ over R, and you just plug numbers in, and this idea here on this page that I'm at where it's like final minus initial, you sort of gotta respect the idea of doing that, and yeah, it's all good. And so this is saved here. This one. 379, 18. That's right. So I probably should have, or it would have been less confusing for me if I had a written page 379 on there. Anyways, but so here we go for 17. Let's jump ahead to that 8B since we were talking about it and so on. 8B down here. What's 8B? So the energy of the system was answered again there. I guess I kind of forgot that I had already done it. And then with the electric potential at each midpoint. So basically, from the midpoint, see how one of my distances now is like this √3 number from doing geometry work to do with the triangle itself. So you've got a 2, 2, 2 triangle, it's equilateral, and you know, so this ends up being a 90-degree in here. So you've got a one here and a 2, and that's your classic 1, 2, root 3 triangle, if you recognize that. Otherwise, you're doing the Pythagorean theorem, which is not the end of the world to have wasted some time doing that. But you know, this certainly would be the 2 and the 1 and the root 3 from a triangle that should be familiar from grade 11 math, where you're talking about special triangles. So it's your 30, 60, 90 triangle. So there's your 60, of course, and there's your half of the 60. So that's the 30 there and 30 there, right? And then your 90. So you can picture the special triangle coming into play there as a you know, way to be able to do this quicker and easier. I have it written there, 1, 2, root 3 triangle. And so then now it does appear though that they asked for electric potential. And oh yeah, because this is, you see how this is KQ over R. So the problem with this solution set right now, this is KQ over R, right? But this is V equals KQ over R. And so I have it mistakenly written as this. So this isn't E, this is V, electric potential. Whew. Good. So see how the answer is in volts. So that was just an oops on my part where I put it in as EE by accident, which it is still an energy concept, right? This is energy per charge. So when I did that solution set, actually this solution set was from more than a year ago. This particular set. So that mistake was made by me more than a year ago, and to be honest with you, fully honest with you, I'm more clear on the distinction between V versus delta V now in teaching this to you guys than I've ever been. I actually was a little bit confused last time. Like I've always been a little bit off on it because it was never. I don't feel it was ever really explained or emphasized to me. But the idea that this really is this one here really is a difference, but it's different from infinity, right? Versus this one is different locally between A and B, right? So they are both voltages. They are both potential differences. But if your difference is relative to 0, then you can just say it's your actual value, right? So if someone wins $1 million, then, you know, if they had no money, then they gained $1 million and now they're a millionaire. If they were already a multimillionaire, they just have an extra million. You know what I mean? They're still a billionaire, but you get the difference there. So is that good? Does that fix it for you, David?
Yeah, that's good. Thanks.
It was just basically just needed to be a V, and to notice, to emphasize that we're talking about this equation for this concept, you know, is critical, of course, right? So in part A, they're talking about energy versus, you know, in this one, we're talking about V, which is still energy, but it's energy per charge. So boom, we did it. We don't have to save it till tomorrow morning. Now that I realize that we were talking about number 18 by accident. That's stressful. All right, we're good. I'm recovering. Any other questions? All right. Number 18, lesson 18, whatever. So we're going to talk about parallel plates a little more. So these are going to be the equations unique to a situation where you have a voltage applied on parallel plates. So this is the explanation of the contradiction when you have a voltage applied. We're going to look at just in general what happens between parallel plates. So in parallel plates, you've got uniform electric fields, right? So it's kind of a special situation. You can do some work that you don't have the luxury of being able to do if it's not uniform force. You know, uniform force gives uniform acceleration, and so of course, like our previous knowledge from grade 11 applies nicely. But in a case where you don't have uniform force, you can't just say, oh, well, you've got acceleration and blah, 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 because the acceleration wouldn't be constant. So that's what we're tackling here. And then also we're going to look at the historical, very important historical experimental result where they determine the charge of an electron. So if you're wondering how they know that the charge of an electron is 1.602 times 10 to the negative 19, this lesson covers it. So here's a set of parallel plates, and I have added in to make it more clear than other where this came from. I think was from the online material. I one semester I decided I was going to like take some of the online stuff. I think I was actually that semester I was teaching it online, but also in course. So I kind of amalgamated the two sets of information. But anyway, so they did not make it very clear in this diagram that there's a voltage applied. So I have shown here, a blue line here showing there's a voltage applied, and I called it delta V, even though in grade 9 we would have just said V and called it potential difference. Now we're being more careful in calling it delta V because it's a local difference between points A and B, right? So your textbook will also even show this as VAB, right? Either way, it's a change, right? So all of these, so this one and this one, they both equal V at 1 minus the other. So let's just say VB minus VA. The potential relative to infinity, the energy relative to infinity at B minus the potential at infinity or 0 relative to A. Anyways, so electric field between those plates, something to know is that is a uniform electric field. And so it's a uniform electric field, and so the work required to move a charge from one plate to another is kind of easy to calculate based on grade 11 stuff, right? Because it's linear, it's uniform acceleration, there's a uniform force, there's uniform force, so there's uniform acceleration. And so we're talking about like this might give you shivers, but the uniform acceleration equation selection matrix could, that would actually work for us, right? Which it's okay if at right now it's kind of a stressful thing, but later on, if you're like working for your PhD and it comes down to determining acceleration, the initial velocity and trying to like displacement and whatever, right? Obviously that's going to be a good thing because hey, I can get a PhD just based on grade 11 physics. Sweet deal. Kind of like I've said this before to students too. It's to do with equations, linear systems, two equations, two unknowns. The first time you do it in grade 10, you tackle it, then you see it again in grade 11. It's like, oh no, not that stuff. But eventually it's going to become, hey, wait a minute, to solve this bigger, crazier problem I'm working on, all I have to do is remember how to do that grade 10 work of solving linear systems. You need to get to a point where that's a good thing rather than a bad thing, having to remember linear systems. So it's kind of the same deal here, right? You got to get to a point where working with uniform acceleration stuff that's like, oh, okay, I can do that. I've already done that before. We're not actually going to be doing that much yet, but basically the idea is there. Just to get you thinking about it. Anyway, so applying this knowledge for electric potential, like an equation for electric potential and whatnot between the plates can be derived. So that looks like this, right? So, this is the same note as before. I just being super redundant and thorough to emphasize things. So remember previously we talked about potential difference right here. Previously potential difference, V voltage was potential difference. Now we're saying V is just electric potential. We're dropping the difference word, right? And we're saying it's energy per charge. And it is still actually a difference though, because it's how different it is in comparison to infinity. And then in comparison to that, we also talk about potential difference between two spots that are close by. And so the two spots close by business is when we say delta V or VAB and all that. So I think that's like the third or fourth time I've talked about that. So that's just this is definitely a recall page here. We've already done this. All right, down here. Oh yeah, so now voltage from a battery is actually referred to as delta V or VAB, VB minus VA, right? So that's why in this equation or this here, I'm actually saying delta V on purpose. Textbook doesn't always though. Anyways, so we know that work done is force times distance, right? That's a known thing from grade 11. So put a check mark beside that, be like, yep, I remember that. And then if a charge if a charge is motion between charge, moving. A charge is moving. Let's try, how do I grammar this thing? Moving. Moving. If a charge is moving between parallel plates with applied voltage, then we have a distance that the charge moves, right? We have this delta D equals R. R is the distance between the plates. So let me just say here, separated by R is the distance between the plates is R. So if the distance between the plates is R, then we're saying, well, and then in my work done formula, delta D is R. So work done is equal F. Now that's actually F dot R. And so this blue note about that is about this blue. It's going to be blue in a second here. Blue dot. And I'm just trying to be really thorough here. We're upping our game to a grade 12 level where we can recognize these things. So these are vectors, right? Those are vectors. So how do we end up with energy as a concept over here, which is a scalar, whatever. So energy is a scalar. And so that's a named mathematical process called the dot product. So we have, oh, actually, no, I'm not talking about that right now. That comes later, I think. Anyways, but yeah, we have the luxury of being able to just talk about work equals force times distance since the force is constant. Okay. I'll mention the scalar product in a bit too, but that's actually called the dot product. So we don't need